Hello. In this video, we're going to go ahead and perform the analysis of a Mosfet DC circuit. And this is a fairly standard configuration for a biasing circuit. It's referred to as the 4-resistor biasing network, fairly common in discrete transistor circuits. But we're just trying to gain familiarity with the different equations and the different parameters of the MOSFET and how they come into play when we're performing circuit analysis. And so for this example, we have the transistor connected to those 4 resistors. I've labeled the resistor connected to the drain RD, resistor connected to the source RS. I have labeled the 3 terminals of my transistor as drain, gate, and source. I have a supply called VDD, positive supply, and then the circuit is going to ground, so just a single supply. And then I've annotated some transistor parameters, the threshold voltage equal to 1 volt, the MOSFET transconductance parameter, Kn, equal to 1 milliamp divided by volt squared. And notice that I've spelled out the value of Kn. Sometimes you may encounter the different values. They'll tell you what the C oxide is, or mu n, width and length. Sometimes they'll just tell you what the value of Kn prime is, and then the aspect ratio, etc. So it's good for you to start becoming familiar with how those relate and how you can calculate Kn based on the different values. And finally, there is a lambda of 0. Notice that if you had a PMOS transistor, normally instead of Kn, you might be referring to Kp, and sometimes for the threshold voltage, you will see it specified also as VTN or VTP, depending on whether you have an N-channel or P-channel MOSFET. The threshold voltage is easy to see though, because for a P-channel MOSFET, it'll just be a negative value. And then we're going to assume that lambda is equal to 0, or in other words, we're going to neglect channel length modulation effects. And we are to find the DC values of the drain current, the gate to source voltage, the drain to source voltage, as well as find out what's the region of operation of the transistor. So for MOSFET transistors, because we have in essence a capacitor at the gate, it's always true that the gate current is equal to 0. And so I can say, in this case I'm dealing with DC quantities, so I'm going to express it as my DC gate current is equal to 0. And that makes the analysis easier because now I know I have a perfect voltage divider between R1 and R2. And so my gate voltage, V sub G, voltage at the gate, is going to be equal to the result of voltage division dividing VDD between those 2 resistors. Since they're of equal value, the voltage at the gate is just going to be equal to half of VDD. So basically 100K divided by 100K plus 100K times 10 volts, that's equal to 5 volts. We can also calculate the current through the voltage divider network, which is going to be equal to the overall voltage VDD divided by the overall resistance R1 plus R2, since they're in series, and that's going to be 10 divided by 200K, or 50 microamps. That's typically, it's not asked in this problem, but it's typically an important consideration for our selection of resistors, as we want to make sure that we are not drawing too much power with our biasing networks. Now, in order for me to start performing calculations, I need to know what's my region of operation, because my equations are going to be different. My equation for ID changes depending on whether I am in the cutoff, triode, or saturation region. Since we are not told which region we are on, we need to make an assumption. And so we're going to assume that M1 is in saturation region. And what's going to happen is we're going to proceed with our calculations based on this assumption, and we're going to get some results. And once we get those results, we can see if the results are inconsistent with the assumption of us being in saturation, then we know that we have made the wrong assumption and we need to go back and change our assumption, maybe assume that we're in the triode region and perform the calculations And at some point, our results are going to match our assumption, are going to be consistent with our assumption, and so we'll know we've made the right assumption. And then in all reality, after you get used to the operation of the transistor, it will become easier to identify when the transistor is in cutoff, triode, and saturation. Sometimes saturation and triode will not be that obvious to distinguish, but certainly cutoff will be. So let's go ahead and, based on that assumption, put out the equation for the drain current, which is going to be 1/2 of Kn times VGS minus VT squared. And we know that VGS minus VT is equal to the overdrive voltage. Now VGS is simply the delta VG minus VS. We have the value for VG. We don't have the value for GS just yet. But we know that VGS is equal to VG minus VS. Oh, and even though all the signals here are DC signals, and so I could write my expressions like this in terms of the overall signal. I'm going just to keep consistency and to stress the fact that these are DC signals. I'm going to use capital subscripts. So I know that VGS is equal to VG minus VS. VG we have calculated as 5 volts. And Vs is going to be equal to ID times resistor Rs by applying Ohm's law. So it's going to be the voltage drop across resistor Rs. ID times Rs. Since Rs is 6 kilo ohms, I could express VGS as being equal to 5 minus 6K ID, or I can simply express the 6 ID where I'm assuming my ID is in milliamps. Either way will be fine as long as you keep your assumption constant. I'm going to say here where ID is in milliamps. Alright, so I can go ahead and write my equation for ID based on this value of VGS as being equal to 1/2 of Kn, which is 1. And again, it's 1 milli, but since I'm going to be putting all my terms in milliamps or in millis, I'll just skip the milli for all of them. Times VGS, 5 minus 6 ID minus 1 squared. And so when I write that in standard form for a quadratic equation, I have 18 ID squared minus 25 ID plus 8 is equal to 0. And there are going to be 2 solutions to the quadratic equation, 2 possibilities for ID. The first one is ID equals 0.89 milliamps. The second one is ID equals 0.5 milliamps. So which one is the true value of ID? Well, there's only going to be one of them, that, if any, that is consistent with the assumption of saturation. And so we're going to go ahead and test both values and see which one is consistent with our assumption. So let's go ahead and evaluate the first solution, where ID is 0.89 milliamps. In that case, my Vs is going to be 6K times ID in milliamps, or 6 ID. So 6 times 0.89. Remember that was 6K times 0.89 milli. The K and the milli cancel out. And that gives me 5.34 volts. Now I have calculated my value for VG as 5 volts. And so if I had a Vs of 5.34, that will imply that my VGS is less than 0. It's a negative voltage. It's minus 0.34 volts. And so this is inconsistent with my assumption, because my transistor will be in cutoff then. So inconsistent with assumption of saturation. So let's go ahead and evaluate the second solution. If ID equals 0.5 milliamps. And in that case, my Vs will be 6ID, or 6 times 0.5, which is 3 volts. And that one is consistent with my assumption. In that case, that will imply that my VGS is equal to 5 minus 3, or 2 volts. It is greater than the threshold voltage of 1 volt, so my transistor is on. And I still will have to see whether it is consistent with saturation or triode by looking at the relationship between VGS and VDS, but at least the transistor is on, so far so good. Now I'll have to calculate my VDS, which is going to be equal to VDD minus the voltage drop across resistor RD minus the voltage drop across resistor RS. That will be the voltage drop across my drain and source of my transistor. So VDD minus voltage across resistor RD minus voltage across resistor RS. Or VDD minus ID times RD minus ID times RS. Or 10 minus ID was 0.5 milli. So I'm just going to do 0.5 and then just skip the case in the resistors. RD was 6, RS was 6. So basically 6 plus 6 is 12, 0.5 of that is 6, 10 minus 6 is 4 volts. So my VDS is 4 volts. And so I can see that my VDS is greater than VGS minus VT, because 4 volts is greater than 2 volts minus 1. And so my solution is consistent with the assumption that my transistor was in saturation, because I'm meeting the condition for saturation. So because of this, I know my transistor is in saturation region. And I think I have calculated everything I needed to. So my ID, I have concluded, is equal to 0.5 milliamps. My VDS is equal to 4 volts, and my VGS is equal to 2 volts. And that's the solution for this circuit. Thank you.